You made it! Welcome to the last clip for Math 406. And our crowning result, our final destination is Jordan form, which most people just call Jordan form. Sometimes it's called Jordan normal form. There's also a rational canonical form, but we're not going to get into that. Let's see. So first off, just a quick corollary from the previous clip. So what we just proved in the last clip is that a nil basis always exists. And so just a corollary of the shape that nil basis takes. If you have a nilpotent operator, then with respect to a nil basis of it, the matrix looks exactly like this form right here. So if you compare to, which one was it? So compare it to 819, which said that we've got like zeros down the diagonal and ones above the diagonal, and actually, sorry, it didn't say that. It just said we've got junk up above. So strictly upper triangular matrix like this, yeah? And so now you can see, we can do better than junk like that. We can do specifically that these guys along the diagonal are 1, or adjacent to the diagonal are 1, and everything else up there in that corner is just equal to 0. Okay, so let's see. So now our next definition is that a Jordan block is an upper triangular matrix that looks like this. So you've got the constant value all the way down the diagonal. So all of this value is the same. It's lambda all the way down. And then above the diagonal, you've got 1s. Everything else in the matrix is a 0. So like the smallest Jordan block you can have is just like a 1 by 1 lambda. And then the next size you can have is lambda 1, 0 lambda. And then the next size up you can have is lambda 1, 0, 0, lambda 1, 0, 0, lambda, and so on and so forth. Okay, so then a Jordan basis for an operator T is a basis in which the matrix is block diagonal and those diagonal blocks are Jordan blocks. And so then the theorem for Jordan form, so this is theorem 860. Is that every operator has a Jordan basis. So I guess I should specify just to emphasize for every complex vector space. Every linear operator has a Jordan basis. So in other words, by picking the basis correctly, you can ensure that any operator has this sort of lambda 1 with 1's block followed by lambda 2 with 1's lambda k m, let's say, and 0 everywhere else. So that's the Jordan form of a matrix, of an operator, or of a matrix, whatever. Okay, so for the proof of this one, and I guess, so I'll just say, so for this one, you should probably compare to 829, which told us that we can do something like this where the AJs look like lambda j down the diagonal and then mystery stuff above the diagonal with 0 below. So just to get rid of most of that mystery stuff right here, that's basically what all of the work we've just done through the last several results has been to accomplish. Okay, so recall that we have this decomposition into nil spaces of V. So, okay, I guess M there. So this is G lambda K, as K goes from 1 through M. And that's the generalized eigenspace or nil space for T. Okay. and this is where the lambda k are the distinct eigenvalues of t. Okay, so if we look at S lambda as t minus lambda I restricted to G lambda, it's nilpotent, right, by the definition of G lambda. So there's a nil basis of each G lambda for S lambda. And then we have that the matrix of S lambda looks like this, with zeros down the diagonal and ones above the diagonal and zeros everywhere else. But that's true if and only if we look at the matrix of T restricted to G lambda, that it be the one with lambdas down the diagonal and ones above the diagonal. And that's just because the matrix of a linear combination is a linear combination of the matrices, and then the restriction to G lambda also can be pulled through the M. So we have this guy, and this guy is a Jordan block. So the nil basis corresponding to S lambda is a Jordan basis corresponding to T. I guess to be precise, T restricted to G lambda. And so then combining these, we get a basis for all of V, and it would, and I guess the key point here, the most important thing that I just naturally left out, is that it is a Jordan basis for V. And we are done. That was the course. Hope you enjoy it.